Okay, so as I said last time, this lecture will talk about the slew rate of a two-stage op-amp with compensation. So in lectures 39 to 41, we had studied slew rates and we had found slew rates for various op-amp configurations. But at that time, we had not studied frequency compensation, and so those op-amps were not frequency compensated. We also saw during these discussions of slew rate that for high gain amplifiers, slew rate becomes a limitation only in closed loop configurations when the bandwidth of the amplifier is very high. So today in this lecture we'll discuss the slew rate of a two-stage op-amp with compensation and which is placed in a unity gain feedback. So this is a discussion about slew rate, which is chapter 9, but because it is done for a circuit that has compensation, it is also chapter 10. Razavi actually discusses this circuit in chapter 10 after discussing compensation. So kind of following his sequence, I am also discussing this after all the other things were discussed already. Alright, so we look at the simple two-stage op-amp with a simple differential amplifier as the first stage. So by the way, this circuit is drawn slightly differently than what is conventionally drawn. Conventionally, the diode connected transistors is drawn on the other side, but to kind of facilitate unity gain connections, as Razavi also does, this is drawn this side. So the output is taken here of the non-diode connected transistor that goes to the input of the second stage, which is a common source stage, and the compensation capacitor is between the input and output of the second stage driver transistor. Alright, so with this, V1, V2 are the inputs, VO is the output. Of these, which one is positive, which one is negative? So from here to here there is a change of sign, from here to here there is a change of sign. So V1 is the positive input terminal, V2 is a negative input terminal. So to create unity gain feedback, we'll short the negative input with the output. So that is what we will do. So this now is a unity gain feedback two-stage op-amp, and now we want to study the slew rate characteristics of this circuit. Alright, let us first put DC values, because in order to do transient analysis with capacitors we must have well-defined DC voltages before and after some switching happens at the input. So we'll say let the DC input voltage V1 be 1.5 volts, and because this is a unity gain configuration with a high gain, VO will also be 1.5 volts under DC conditions. Let us make VO1 as 2.4 volts. That is in some sense by symmetry, because if M4 has a 2.4 which is a VGS, then M3 will also have M4 has a VGS of 0.6, then this node will be at 2.4, so we'll say this is also at 2.4. Actually we'll assume that there is some common mode feedback provided so that the DC value of this VO1 stays at 2.4 irrespective of the input, which is a reasonable assumption. Actually we had seen this also in a different context for a two-stage op-amp, which I forget which lecture it was, but anyway, so we'll assume that the DC value at VO1 stays at 2.4 irrespective of the DC value of the input voltage. Alright, so then the capacitor voltage, which is VO1 minus VO, I have defined it as plus minus, so VO1 minus VO is 2.4 minus 1.5, so 0.9 volts. Let us also assume that ID1 is 1 milliamp. So ID1, ID2 are 1 milliamp. So 2ID1, which flows here, is 2 milliamps, and this current in M7 and M6 is also 2 milliamps. Alright, so this is 2 milliamps, this is also 2 milliamps. And as we did with slew rate analysis before, we'll assume that all the MOSFET capacitances are negligibly small. So the slew rate is determined basically by the compensation capacitor, which we'll assume to be large compared to MOSFET capacitances. Alright, so now let us apply. So we'll calculate both positive, not calculate, we'll derive expressions for the positive slew rate and negative slew rate. So positive slew rate is when the output goes higher. So for our unity gain feedback, we'll make the input also go higher. So let us apply a step input of from 1.5 volts to 2.5 volts at some time t equal to 0. Right, and we want to analyze this circuit. So the input was 1.5, at t equal to 0 it is suddenly stepped to 2.5. Now, as we've done before, while doing slew rate analysis, it is good to first start by looking at the circuit as t tends to infinity, which is the circuit when it goes back to a new DC state after the input was changed at t equal to 0. So as t tends to infinity, the input voltage is 2.5. Therefore, the output voltage will also be 2.5. It's a unity gain amplifier. As we said earlier, we'll assume that VO1 stays at 2.4 independent of the input. So we have 2.4 and 2.5. So VC, which will be VO1 minus VO, which is 2.4 minus 2.5. So minus 0.1 volt. So for t less than 0, VC was 0.9 volts. Now, after the switching happens, eventually VC will be minus 0.1 volt. So this capacitor must discharge from 0.9 volts to minus 0.1 volt. Alright, so there must be a discharging. So current has to flow out like that of the capacitor. Alright, now let us analyze a circuit at t equal to 0 plus, which is what will give us the slew rate. So at t equal to 0 plus, V in 1 has changed to 2.5. VO is still at 1.5 because VO will not change because of the capacitor. We'll see. For now, let's assume that it's not changing. The capacitor voltage, of course, will stay at 0.9 because the capacitor voltage certainly will not change instantaneously. And so VO is 1.5, VO1 will be 2.4 volts. Alright, so we have V in 1, which is 2.5, VO is 1.5. So V in 1 is much higher than the gate voltage of M2. So M2 will turn off. And if M2 turns off, M4 doesn't carry current, and if M4 doesn't carry current, M3 doesn't carry current. So M2, 3, 4 are turned off. Alright, so here is the circuit. So the M2, M3, M4 are turned off. This current, so earlier for t less than 0, this was 1 milliamp, this was 2 milliamps. Now V in 1 has increased. So the source voltage of M5 has increased. So M5 will stay in saturation. Therefore, it will continue to carry 2 milliamps. So M1 will adjust its gate source voltage so that it also carries 2 milliamps. Alright, so 2 milliamps will flow through M1 down. Okay, let me put the arrows. Alright, so there's 2 milliamps flowing here. 2 milliamps flowing here, that has to flow this way, it has no other place to flow. So that flows up through the capacitor, so the capacitor is discharging. Alright, so that current has to come from here and that current has to come from M6. Alright, so this is the current path for the current to flow. But there is a current flowing in M7 also. Because M7 is on, nothing has happened to M7. VO is still 1.5 volts. So this is all at t equal to 0 plus. So M7 is carrying its saturation current. M6 is carrying its saturation current. So how much current is flowing where? This is a little tricky, right? Because this is 2, 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 but this is 2 and this is 2 also. So how can be this be 2, this be 2 and this be 2? Something is not right, right? So you think what must be happening here, all right? It's very fascinating actually. In fact, this is the first time we are encountering it this semester. All right, let us see. So what this means is that M6 must supply 4 milliamps of current, because 2 milliamps goes this way and 2 milliamps goes that way. But the saturation current of M6 was 2 milliamps. The only way the current in the saturation current in M6 can increase is if VO1 becomes lower. This is fixed 3 volts. If VO1 becomes lower, the source gate of M6 increases and the current can increase. But can VO1 increase? There is a capacitor here. Interestingly, VO1 can increase, decrease. VO1 must decrease so that the source gate voltage of M6 increases. Can VO1 decrease while keeping Vc constant? Again, we are talking at t equal to 0 plus. At t equal to 0 plus, Vc is whatever it was, 0.9 volts. The only way VO1 can decrease is if VO decreases by the same amount. Then Vc remains constant, VO1 becomes lower, M6 can supply a larger current, and everything is, all the laws of electronics are satisfied. So that is what happens in this circuit. At t equal to 0 plus, VO1 suddenly drops. VO also suddenly drops, so that Vc remains constant, M6 supplies 4 milliamps of current. And then the slew rate of the circuit is this current, which is 2 milliamps, which is actually 2ID1 divided by the capacitor Cc. So the slew rate, the positive going slew rate of this circuit is 2ID1 by Cc. All right. So here is a SPICE simulation of this circuit. Let us quickly look at it. So this is VO1, the blue. So the blue was 2.4. So the switching is happening at this point in time, 1 nanosecond. So before 1 nanosecond, the input voltage was 1.5. At 1 nanosecond, it is made 2.5. So this is the time of transition. So VO1 suddenly drops. All right, VO1 suddenly drops at this point. Vout, which is red, also drops by the same amount. All right, so that Vc, which I have not plotted, stays constant at 0.9 volts. All right, the current ID of M6, the green one. So then this is the ID of M7. So both of them were here, which were about 2 milliamps. So they were both equal for t less than 1 nanosecond. At t, when the switching occurs, the M6 suddenly starts carrying twice the current because VO1 has dropped. All right, and because of this, the capacitor current, which was 0 before switching, suddenly starts carrying a current, and it's a constant current for some time, and that constant current charges VO, and so slope of this line is actually the slew rate. All right. Okay, let us see the negative. Okay, one comment. So this is a very simple analysis because we assume that only Cc was present. In real circuits, there will be a load capacitance at the output node, which is more often than not of the same order as Cc, in which case we have two capacitors that we have to think about while analyzing for slew rate, Cc and Cl. And if Cl is present, then so here we said that, well, VO will suddenly jump, I'm sorry, V out will suddenly reduce at t equal to 0. But if there is a CL, it will not allow V out to change suddenly. Then the analysis becomes much more complex and we will not study it in this course. Alright, this is far too advanced for our course, especially because we've hardly done any transient analysis in the course. Okay, but you can think about it if you are adventurous. Alright, let us look at the negative slew rate. So now we say let at t equal to 0, V in 1 suddenly change from 1.5 volts to 0.6 volts. Alright, so I'm saying 1.5 to 0.6. So the reason I'm making it 0.6 and not 0 is we still want the circuit to continue to work as a unity gain amplifier, which means that all transistors must stay in saturation even after switching occurs. If we make this 0, M1 will turn off even in the final DC state, and that will become a very different circuit and very complicated to analyze. So this way we maintain linearity. Alright, so with this we say first we find voltage is at t tending to infinity. So we say if the input is 0.6, then the output is also 0.6 as t tends to infinity. We'll keep VO1 at 2.4 and therefore VC, which is VO1 minus VO, which is 2.4 minus 0.6 equal to that is not, I'm sorry, this is, how much is 2.4 minus 0.6? It's 1.8 volts. Okay, so this is 1.8, this is 1.8. Alright, that is a small mistake, that's okay. Alright, so VC must charge from 0.9 volts to 1.8 volts, which means that current must flow from VO1 to VO in CC. Alright, now let us look at t equal to 0 plus. So at t equal to 0 plus, V in 1 has become 0.6. VO still has its earlier value of 1.5, or let's for now assume it is, maybe it is jumping, we'll see if it is jumping or not. VC stays at what it was, 0.9 volts, the capacitor voltage, and VO1 therefore is 2.4 volts. So V in 1 is 0.6, VO is 1.5, so M1 will turn off because its gate voltage is much smaller than the gate voltage of M2. So M1 turns off, so let us draw the circuit. M1 turns off, M5 is carrying 2 milliamps, so now M2 carries 2 milliamps, M4 carries 2 milliamps. The 2 milliamps of M4 is mirrored by M3, so M3 carries 2 milliamps. That M3 current flows through the capacitor and it charges the capacitor. Alright, and that 2 milliamps flows through M7. M7 was already carrying 2 milliamps, so that is good. But what happens to M6? M6 should also be carrying 2 milliamps. But now it looks like M6 should carry no current. So actually I don't think this pause is required, because as you can guess, what's going to happen is VO1 is going to jump and VO is going to jump. Both are going to jump up so that the source gate of M6 drops and M6 carries no current. Alright, so that is what will happen. So here is the simulation result. So VO1 is, so the switching occurs at this point, 1 nanosecond. So before the switching, VO1 was 2.4, V out was, okay, here it is 1 volt, it doesn't matter. It could be 1.5. Okay, I've made it 1 volt, not relevant. Both are jumping up. So VO1 jumps up from 2.4 to nearly 2.55. So M6 turns off. So ID6. So ID6 was here, ID6 and ID7 both are here, about slightly greater than 2 milliamps. At the point of switching, ID6 suddenly goes to 0. Okay, it has become 0. ID7 continues to carry its current, and that current is flowing through the capacitor, there is a slight difference in this current. Okay, I'm sorry. So ID6 is not going to 0, by the way. So this is green is here. So ID6 is not becoming 0. It is carrying a small current, 0.1 milliampere. So the current in the capacitor is slightly less than the current in M7. And that is what charges the capacitor. So let's go back here. So of course this is these 2 milliamps are without lambdas and all that. So the simulation show that this current is slightly larger than the capacitor current. M6 carries a certain current, and the current here actually is what determines how much M6 will carry. Okay, so it turns out that with all the lambdas, this current is slightly less than 2 milliamps, and therefore the current in CC is slightly less than 2 milliamps, and that current is continuing to flow in M6. Alright, so that is what is happening. Now that is up to here. Okay, so what is happening here? So let us see, the capacitor current is this. So it's more or less constant. This slight change is due to channel length modulation. And this time, so V out is dropping. There is a linear discharge at V out. And that is what determines the slew rate. Now this is when the slew rate regime ends and the circuit goes into a small signal linear operation during the transient, and that is when all the currents and voltages are behaving exponentially. Alright, so we are not looking at this. Actually I should have mentioned this before also. Let's go back, I should mention it. So no, okay, it's not happening here, so it's okay, it's not happening. Alright, so that is what is happening. Okay, alright, so that is that. Now let us ask one more question. Suppose, so when we did this analysis, we assumed that this current is 2 milliamps, this current is also 2 milliamps. Roughly speaking, what happens if this current is not equal to this current? Alright, then the analysis is much more complicated. So we will not discuss it. I'm just going to show one SPICE result for the case when ID5 is greater than ID7. Alright, so let us just see what happens here. So what we are saying is, if this is 2 and this is less than 2, this current is less than 2, what happens? So the M7 cannot carry 2 milliamperes. Let us say its saturation current is 1 milliampere. Then what happens? Then 2 milliamps cannot flow here because M7 can support only 1 milliamp. So if this, then that has to be 1, this has to be 1, this has to be 1. So what happens? Let us just see. You can probably guess, right? So you have a current path M3, capacitor M7. The saturation current of M7 is smaller than the saturation current of M3. So what will happen? M3 has to go into triode. Let's see if that is what happens. So M3 is the drain voltage of M3 is VO1. So let's see. So okay, so this is a point of switching. So VO1, so it was 2.4 earlier. Suddenly it is going up to greater than 2.8 volts. Alright, that does two things. That turns M6 off. If this is 2.8 volts, the threshold is 0.4. So M6 turns fully off. But this about 2.8 causes M3 to go into triode. Alright, and therefore the current in M6 is this green, which has become nicely 0. The current in M7 is this. It is continuing to flow about whatever it was earlier. So in this case it is some 1.7 milliamperes. And that current is the current in the capacitor also. This purple is the capacitor current, which is overlapping the M7 current, and that is what charges the capacitor and causes a V out to drop linearly with time. Alright, so in fact this is where I wanted to make the other comment. So something strange is actually happening at this point. Alright, So this initial slew rate is okay, but then once the transistors go into small signal linear operation, all kinds of things are happening. All kinds of weird things are happening. As I said, we will not discuss them. This is a little advanced for this course. So, but this is this we can understand. So, we should be aware of. All right. Okay. Okay. This actually ends this course. I'm finished. This is actually the last week of the semester, and we have completed basically chapter 10. There are a couple of more things in chapter 10 that I'm not discussing related to advanced techniques for frequency compensation, because I think it is becoming a bit of an overload at this point and it's not required. Anybody is interested in anybody actually wanting to do frequency compensation in a real life project, you will be able to learn it yourself from all the fundamentals you learned. All right, so this is the end. This is the last lecture of the course. All right.